When I saw that Mike Shara was coming to speak, it reminded me of a story from some years ago about a clever and witty but uneducated man all of you will have heard of, Muhammad Ali. He maybe didn't have an education, but he was clever. And he was on a flight one day, taxiing for takeoff. He was flying first class, of course, when the stewardess making her last-minute checks looked down and saw that he didn't have a seatbelt on. So she said to him, "Sir, please, we're about to take off. Put your seatbelt on." And Muhammad Ali looked up at her and gave her that impish little grin that he had and said, "Well, Superman don't need no seatbelt." And he had met his match. She smiled sweetly down at him and said, "Sir, Superman don't need no airplane." Now, we know he wasn't really Superman, but we have a scientific Superman with us this evening. Mike Shara has had an amazing career of productivity, outreach, administration, and I just want to tell you a little bit about that before you hear him talk about Einstein this evening. Mike is Canadian, and that's a good thing. We've discovered that we're probably not related. He originally comes from Quebec. My Canadian family's Ontario, and those are very big provinces, so there's a bit of separation. Mike was an undergraduate at McGill University to start with. Now, McGill is ranked in the top 40 in the world. It's an absolutely outstanding university, but it wasn't quite good enough for him. So he moved to the University of Toronto, which is in the top 20. And after his undergraduate degree, he then started his PhD at Toronto, but his supervisor left. Now, that happens to students. Students out there, this can happen to you. And so Mike, in searching for another supervisor, found an absolutely brilliant supervisor in Gergi Shaviv at the University of Tel Aviv. And so in September of 1973, he set off for Tel Aviv to do his PhD. That was just days before the 6th of October, 1973, when the Yom Kippur War started. And of course, faculty and students at the university are also soldiers. And so the university does not continue teaching new graduate students when the war starts. So Mike was planting crops at the end of the runway with bombers and jets flying over his head for a few weeks before he got his degree program started. I think that's an unusual start to a PhD. After some postdocs, he ended up at the Space Telescope Science Institute, where he was for 17 years, and many astronomers on the planet considered him to be the most feared astronomer anywhere, because he ran the committees that decided who got the Hubble Space Telescope time. Now, Mike was not actually the guilty party who made that decision, but of course he was in control of the process, and some people did consider him to be the person responsible. Some thankful, some quite viciously otherwise. After many years there, he moved to the American Museum of Natural History. Now, there are some great natural history museums on the planet. Chicago, the Smithsonian in Washington, Paris, but in my opinion, the top two natural history museums on the planet are our own Natural History Museum in London and the American Museum of Natural History in New York City. Mike is curator of astrophysics there, and that may not immediately mean something to you. What it means is he's a senior professor. That's a professorship, and it is a research institution. The reason he's here now is he's here as a distinguished visitor. Our own Joanne Bibby from the Jeremiah Horrocks Institute. Where'd you go, Joanne? Oh, there you are, over there. Was a postdoc with Mike for 2 years at the American Museum before she came here, and she has organized for him to visit us as a distinguished visitor, and we've happily talked him into doing this talk tonight. Now, Mike is mostly a researcher, but 20% of his time is devoted to preparing programs for the museum, which are often seen by millions of people. And I believe that this talk tonight grew out of one of the programs that you developed for the American Museum of Natural History. So we've all saved a flight to New York and having to crowd in with 1 million people to hear this talk tonight. I'd just like to tell one little story that Mike told me nearly 30 years ago. He probably doesn't remember this. And I think it illustrates, especially students or parents of students, why a scientific education is so important. Not everybody needs to be an astronomer, but astronomers know how to solve problems. And Mike said that when he was working in Israel, somebody came to him with a problem that needed solving. It wasn't astronomical. They were importing tiny chips of industrial diamonds from a country I won't name, and the suppliers were salting them with about 10% zircons. and these little tiny chips. I mean, ladies, if you've got a nice big diamond ring on your finger, you can probably tell the diamond from a zircon. But when they're practically microscopic in size, how do you get rid of the 10% that are not diamond? So that was the problem set for Mike. And being a clever scientist, he just looked up the density of diamond and zircon, found that zircon's denser than diamond, went to the Merck index of chemicals and found a liquid that had the density between the two and said, right, get a puddle of that and chuck your stuff in and the diamonds will float and the others will sink. Problem solved. I think that's a nice illustration. Mike's research has been very, very broad. He's kind of had a theme of things that blow up running throughout his entire career, and he's got a vast number of publications. Supernovae, novae, cataclysmic variable stars that orbit each other in periods of hours and go nova. I think you started your career crashing stars into each other theoretically. White dwarfs crashing into small hydrogen-burning stars. And he's worked on brown dwarfs and cool stars and exoplanets and, well, being all, how many orbits of Hubble have you had? Yeah, how many orbits of telescope time have you been PI on? Close to 1,000 orbits of Hubble time as PI. That's practically the entire 25 years of the mission. No, it orbits in 90 minutes, but that is a lot of Hubble Space Telescope time. So as you can hear, Mike is very, very illustrious. I think he's also a very good speaker, and the topic tonight is of interest to us all. Please, will you, with me, welcome Mike Shara.
How about now? Can you hear me? Wonderful. Okay. Well, Dawn, thank you for that extraordinarily kind introduction. I really am very grateful for it, and I'm delighted to see so many of you here this evening. Thank you so much for coming. What I do want to talk about tonight is this extraordinary man, Albert Einstein. When you just look at this cartoon, you know where he's going. You don't really need me to tell you what's going to happen next here. What I want to do this evening is spend close to an hour with my time evenly divided between Einstein, the man, the human being, his life history in a sense, and Einstein, the scientist, and the science that he brought to us. And I hope that you'll agree with me at the end of the talk that he really was the person of the 20th century. His contributions to science and to humanity really were not matched by any other human being in his time. And the effects that he has had on us, on our civilization, are so profound that had he not lived and had these extraordinary discoveries not been made, it might have been a century before, in many ways, our modern technological society got to where it is today. Let's see if I can master this technology. Yes. So I was very, very lucky in that in 2001, 2, and 3, I was able to get hold of most of Einstein's papers and some of his personal effects. When he died, he left them all to the Hebrew University of Jerusalem, and one of the trustees of the American Museum of Natural History is also a trustee there, and so I was able to borrow all of these wonderful things. And I can say that one of the great thrills of my life was holding E = mc squared in my hands. Now, they were my gloved hands, and there were several people watching me, ready to kill me if I did the wrong thing with them, but I've managed to do that. So I'm going to tell you about his science and his life, and there are, of course, hundreds of great quotes from Einstein. This is one of my favorite ones, that the most incomprehensible thing about the world is that it is at all comprehensible. The fact that this kilogram or so of gray matter is able to make sense of, with a set of tools that we don't really understand why they work so well, namely mathematics, that we can make sense of the universe and do something extraordinary, which is predict the future. Now, nobody in this room, myself included, of course, can predict what's going to happen with the stock market tomorrow. Certainly not the weather here in England. That's utterly unpredictable. But there are many things, the motions of stars, planets, and galaxies amongst them, and in some sense, the decay of particles at the atomic and subatomic level that can be explained, and this is the person who brought us really into the future and pointed the way into the future from the really simple beginnings, extraordinary and beautiful beginnings that were laid out by Newton and his contemporaries, and then we made a quantum leap when this man came along. So what I'm going to talk to you about today is relativity and much more, because that's what he is responsible for, how it impacted our world. He was a human being. He had 2 wives, 3 children that we know of, more mistresses than I can count. He played an important role in the era of McCarthyism, when the United States went a little bit crazy in the early 1950s. He was both a pacifist and a humanist who died with an FBI file that is nearly 1,500 pages long. You can look it up online. Go to www.fbi.gov. He was very anti-war, and yet many people think of him as the father of the atomic bomb. A terrible connection, something that he felt horrific about for much of his life, and well, for the last 10 years of his life, and I'll explain how that happened. He advocated a unified world government. This did not win him a lot of friends in the American government at all, and so he was regarded for many, many years as persona non grata, and many of the either committees or projects that he might logically have served on were things that were kept absolutely secret from him. And finally, he wrote letters about Israel and the Arabs that could have been written today. They resonate today, and they speak for the need for dialogue and understanding and giving on both sides. An extraordinary man. Well, that could have been the title of the exhibition, Great Physics, Great Humanity. We simply called it Einstein. And one of the things that at our museum we do, of course, is we have to market our exhibitions. We're in the 21st century. People don't just come to us because we're the American Museum of Natural History. So we do a lot of investigatory work first before we spend the millions of dollars to put a major exhibition on display. And so we did a survey of our public, several thousand people, and we asked them, what do you know about Einstein? What do you think about Einstein? And what we got over and over again was that he was the father of the atomic bomb, and in this cartoon you sort of see that. There's the nucleus, I guess, that's about to explode on you, and there's the mushroom cloud in the shape of his hair. And people had heard, most of them had heard of E equals mc squared, though very few could tell you what it actually meant. And that was largely what people knew of him. Well, they were right about his hair. They got that part right. And one of the best artifacts that I was able to take from the archives and assemble about him was a letter from a little girl who lived on Central Park West, right next to the American Museum of Natural History. Einstein received about 100,000 letters during his life, all of which are cataloged and what have you. But one of his favorite of all time is this one from Ann Cosin, who said, "I'm a little girl of 6. I saw your picture in the paper. I think you ought to have your hair cut so you can look better. Cordially yours, Ann C. Cosin." And unfortunately, I've never been able to track Ann down. She would probably be, oh my goodness, in her 80s or 90s now. Well, many, many cartoons about Einstein. This one, very appropriate, from some single-celled creature to something that is trying to poke its head out of water to one of the early vertebrates, a caveman, Einstein, and then the descent straight downhill. Who knows what he's watching? How famous was he? Well, this is a letter sent to him from Indonesia to Mr. Einstein, the atomic scientist, USA, and it was delivered. Of course it was delivered in about 3 days. The post office knew exactly where he was and how to find him, no problem. at all. Now, he was on the cover of Time magazine about 13 or 14 times, just about as much as anyone. And it's really interesting to watch the progression of his image in the public media. So here in, back. Here in 1949, we have him as the father of the atomic bomb. This is just 4 years after Hiroshima and Nagasaki. The atom bomb and soon the hydrogen bomb were just consuming the American public and I think the public around the world. So in 1951, and he's still alive, of course, he's seen as the father of the atomic bomb on this cover. In 1979, 100 years after his birth, his centennial year, and of course now he's been dead for about 24, 25 years in this middle image, what you see are planets, stars, and galaxies emerging from his brain. Okay, and so the vision has gone from father of nuclear weapons to the arch cosmologist and the great physicist. And then in 1999, he becomes person of the century, and he's now been transformed into Saint Einstein. He's a religious figure. He's become a religious icon of sorts. Someone who is almost deified by physicists too. We're just as guilty as the public, really. And someone who has these sad, very deep, all-knowing eyes, and it's essentially impossible to penetrate through to this godlike figure. And that was something I really wanted to change. The whole idea behind this exhibition, and one of the key ideas of this talk is, this was a highly approachable human being. Yes, he did physics at a level that no one had ever done before, and he elevated us all, but he was also an extraordinary human being with very deep perceptive powers, and he was also a media superstar way ahead of his time. He understood the media and he played them like a violin. He had, which he played himself, very badly I might say, he had great ideas. He wanted to get them out there, and he knew that the only way he could succeed was by using the media. And he was a master. He was way, generations ahead of his time in using the media to get his ideas out. Well, he was a little boy at one point, believe it or not. You know, he wasn't born with that great head of hair. Here he is at roughly the age of 3. He was born in Ulm, Germany, to Jewish parents who were culturally Jewish, not religious or Orthodox in any sense of the word. And they gave him a lot of freedom, but they also expected things of him. Here, sorry. And what they expected of him was pretty good performance in school. Now, you may have heard that he was dyslexic, you may have heard that he was a poor student, so on and so forth. Nonsense. Here is his high school leaving report card. 6 is the highest possible grade. So in physics, he did get appropriately a 6. In history, a 6, chemistry, a 5, natural history, a 5. I wish he'd gotten a 6 in natural history, but that's not bad. I can't complain. And it turns out that he really was a lovely student, a very, very good student, not much of an artist perhaps, but very, very credible. He went on to do a series of more and more advanced degrees, and not with his parents present. When he was 15 or 16, his parents decided they needed to leave Germany and they wanted to partake or be part of the internet revolution of the age, which was electrification. Electricity was now understood well enough to build generators, and everybody was tired of gas lamps or candles, and so Europe wanted to be electrified. His father and his uncle set up a company. They were engineers, and they built large generators and moved to northern Italy to start electrification processes in some of the towns there. They didn't do terribly well. They went bankrupt. That's another story. Einstein did not want to move with his parents to Italy, and he hated Germany. He was very, very unhappy there. He felt it was much too militaristic a country. Even at age 15, 16, when he would see soldiers marching by in the street, he would run and hide. He was terrified of the military, had no desire to serve. And so his parents allowed him to move to Switzerland when he was just 15, 16, and go live with a family that were family friends, had been for a long time. It was there that he met and fell in love with his first love, a woman, the daughter of the household. She was 2 years older than him. And as much as he fell in love with her, she fell even more in love with him. And he had a very hard time in the end distancing himself from her because he desperately wanted to study physics. And he felt that if he were too entangled emotionally, okay, it would be very, very difficult for him to focus on his studies and get on with the real job of learning physics. And so there's a lot of back and forth between them. And you see that there is, I think, some heartbreak, and this may have been his first heartbreak and perhaps his last. He did eventually settle down with and marry Mileva Maric, a Serbian woman who was the only physics student in his class, in his graduate school. She became pregnant by him. They weren't married, and this was a very, very bohemian thing to do in 1900. She went off to live back to live with her parents and to have the baby while Einstein continued at school. And the baby, a little girl, lived to age 2 and then vanished. And we don't really know what happened to her. Historians of science have gone tramping through graveyards all over Serbia looking for traces of her. There are 2 brief postcards that only became available to historians of science around 1980-85, and in it there is a hint that something is going very seriously wrong with the child. She had some medical condition, we don't know what it was, and either was so badly mentally damaged or died that she was given up either for adoption or buried. Again, we don't know. Mileva returned to school and unfortunately failed her qualifying exam. She tried twice, couldn't get through. She and Albert married, and at first she was extremely happy because she was his sounding board, and then Albert grew more and more distant. They had 2 sons. Here they are with their first child. And initially in their relationship, it was a very loving one. And I ask every woman in the audience, if your sweetheart started a letter to you like this, wouldn't you feel wonderful? My little kitten, he writes to her. And then he continues, I have just read the most marvelous paper on the production of cathode rays by ultraviolet light. Well, you know, she might have found that pretty sexy too, because she was a physics student. So, you know, Albert might have been onto something here. I'm not going to do the full general relativistic field equations, okay? But neither am I going to just tell you in the very broadest broad brush strokes about how general relativity works. I'm actually going to explain it to you, okay? I'm going to make myself do it while standing on one leg, by the way, so I'm not going to go on for too long. But you're going to understand why the Earth goes around the sun and why the clusters of galaxies that we see in the universe don't fly apart by the time I'm done. At least I'm going to try. So what are the implications of his work? Why do we really care about Einstein, ultimately? Okay. Well, he tackled a few little problems in physics, namely light, matter, time, energy, and gravity. And if you don't understand these things, there's no way you can ever understand how molecules work, how your DNA works. You certainly can't do genomics. Forget about it, okay? So that branch of human endeavor remains a black box forever. Electronics, does anyone here by some chance have a cell phone? Okay. Well, thank Albert. I bet most of you have laptops or computers at home, right? Thank him. Fission, the idea that we could have both bombs and nuclear power comes about not directly because of him. Of course, there was experimental work going on in Germany in 1938, the first observations of fission. But in the end, if you didn't have E equals mc squared, you had no idea what was going on. You just couldn't make any progress. And for an astrophysicist, you know, we look up at those little lights in the sky, and until the 1930s, we didn't know anything. I mean, we had a rough idea how far away a few of them were. We had some idea of their luminosity. We had a close-by example, namely the sun, but nobody knew what powered the sun. You know, there were serious discussions in the 1800s about what the power source of the sun was, and if the sun is half coal and half oxygen, well, then the age of the sun is about 5,000 years. The geologists tell us that that's crazy. Maybe the geologists are crazy, because nothing can make the sun go on for 1 billion years, which is what the geologists are telling us. And finally, if you want to understand the universe, you simply have to understand gravity. You have to understand what makes it work. And he told us what makes gravity work with a set of relatively simple equations, not as simple as gmm over r squared, not as simple as Newton, but with much more predictive power, testable predictive power, that in fact has been demonstrated to be extraordinarily right, fabulously beautiful, and understandable in a sense that Newton's laws aren't. Newton's laws are given, okay? Gmm over r squared is just gmm over r squared, whereas Einsteinian gravity has a basis in geometry, something that you can physically understand in your guts, as we'll come to shortly. Now, the human part of him is more complicated. As I said, he was a pacifist who was labeled the father of the atomic bomb. I think he's more the godfather, but nevertheless, he was certainly in the family. He was always a socialist who, during the Second World War, was a staunch supporter of the United States and of its military, because he thought that the Nazis represented the greatest threat to humanity that had ever occurred. He was a person who died, as I said, with an enormous FBI file, and an anti-McCarthy person who was also this staunchly pro-American person. Not religious in the slightest, who was a strong supporter of the nascent state of Israel in 1947, 48, 49, and is the founder, one of the founders of the Hebrew University of Jerusalem. And finally, if you ever met him, you would think of him as a very warm and gentle and easygoing person with a lovely laugh and a sense of humor, who also had the most chaotic family life that you can possibly imagine. So a set of many, many contradictions. Well, 1905, by 1905, he had been working for about 8 or 9 years, very quietly as a patent clerk. That was the only job he could get. No one would hire him as a teacher or a professor, because none of the professors who had been his professors during his PhD could tolerate him. Einstein went to lectures only when he absolutely had to, usually copied notes from his friends, and invariably when they would assign some sort of problem set to him that would require many, many pages of long, tedious calculations, he would delight in finding a much simpler, much more elegant solution that required 4, 5, 6 lines based on modern physics and hand it in. Say, look, that's the answer. That's just the way it is. And that wasn't what his professors wanted. They wanted the long, tedious calculations. So he had no friends in the academic community, except for Marcel Grossman and a couple of his other peers, but none of his teachers. Well, in 1905, after thinking and working and writing only to himself for those 8 years, he came up with explanations for Brownian motion and the photoelectric effect, things that had troubled physicists for many, many decades, and he invented special relativity basically out of thin air. What we see here is his Nobel Prize, which was awarded in 1922, and it's important to note that he wins his prize for den fotoelektriska effekten. He won his Nobel Prize for his explanation of the photoelectric effect. Now, the photoelectric effect gave rise to vacuum tubes. Vacuum tube technology gave rise, in some sense, to the computer revolution of the time, which was cheap radios. You could put a radio anywhere, and it would be pretty much bulletproof relative to the very crude crystal radios that had existed before. So this was a very practical technological application of his work on the photoelectric effect, and the Nobel Committee was sure that it was right. Everyone agreed that his explanation of the photoelectric effect was correct, and so they weren't taking a chance. Relativity, on the other hand, scared them to death. It was scary stuff. Now, the mathematics is only algebra. There's nothing but algebra, okay? At age 13, 14, 15, kids who are studying mathematics know enough mathematics to understand all of special relativity. The ideas behind special relativity were ridiculously revolutionary and very, very scary. That's what terrified the Nobel Committee. And they were afraid that if they awarded the Nobel Prize for relativity, it might be shown to be not quite right. Who knew? And so they took the easy way out. Einstein laughed at them, and when he gave his Nobel lecture, talked only about relativity. Now, for those of you who are lactose intolerant, you should look away, because what I was showing you there was a drop of milk under a microscope slide. Let me see if I can make that, work again. Back one more, forward. Yes. Each of those is a 10-micron globule of fat suspended in water, which is what milk is. So if you don't like milk, you have even more reason to not drink it now. But this is called Brownian motion after the British biologist, Brown, who first noticed that if you suspend pollen grains in water and look at them under a microscope, they jiggle like crazy. They don't just sit there, but they're always jiggling. They're always moving. And there was no good explanation for this. The pollen grains aren't alive. The fat globules certainly aren't alive. So what's going on? Why are they moving? Yeah, I mean, physicists worry about stuff like that. That's just the way it is. That's what we do. We need to understand it. And Einstein came along and said, hey, guys, there are molecules. Water is made of molecules. There are smallest water particles, and the particles are crashing into each other millions or billions of times a second. And by statistical fluctuation, if you take any one of those little fat globules during any 1/100th of a second, you get hit more on this side, so you move that way. Then you get hit on that side. And then maybe 1/100th of a second later, you get whacked by a few more molecules on this side, and so you move that way. And you move up and down and sideways and so on. Now, that's a lovely explanation. And if that's all it were, that's all it were. It would be a possible explanation for Brownian motion. But in fact, he said, okay, now let's do a little bit of math. And when he did the math, he came up with the mass of the water molecule. He was able to tell us what a water molecule must weigh, what its mass must be, and what its size must be. It was an astonishing coup that he could pull this off. And he was also able to explain, using largely the same mathematical framework, viscosity. He could explain viscosity in a way that no one ever had before. And most important of all, he made predictions about viscosity that were tested 2 years later by the French physicist Perrin and shown to be exactly right. So it was clear that we finally had proof that atoms and molecules exist. The Greeks had hypothesized this 2,500 years ago, but one of the truly great intellectual leaps forward was the ability to explain complex macroscopic phenomena and derive from them the masses of microscopic quantities. Again, this is 50, 60, 70 years before the invention of the electron microscope, which finally does show atoms. You can actually see them. So the inference that atoms exist and their size and their mass was a colossal step forward in understanding. There's his Nobel medal. And his true greatness, where, you know, if he had only explained the photoelectric effect, he would always be remembered in physics as one of the, you know, in the pantheon of great physicists, the 100 greatest or whatever. But he tackled the problems of space and time. He demonstrated that energy and matter are the same thing. Energy and matter are the same thing in the same way that, say, US dollars and British pounds are the same thing. There's a conversion factor between them. Today it's about, I don't know, 1.5, something like that. So you can write down an equation that is 1 British pound equals 1.5 US dollars. They're the same thing, and the conversion factor is 1.5. Einstein wrote down that energy equals mass. Just like pounds equals dollars, energy equals mass. The conversion factor isn't 1.5, okay? It's c squared, the speed of light squared, and depending whether you use CGS units, MKS, doesn't matter, it's 1 with 21 zeros after it. So it's not 1.5, it's 100 billion, billion, billion. Okay, this really, really, really large number. That's the great discovery that eventually explains nuclear energy, the bomb, stars, and so on. Namely, that a tiny little bit of mass, unfortunately just a kilogram of mass, can release enough energy to knock down a city or power that city for decades. Now, remember that cartoon I showed right at the beginning, E equals ma squared? Nope, that's wrong. E equals mb squared? Nope, that's wrong, okay? You know where he's going. He's going towards, of course, E equals mc squared. And that cartoon actually comes from, from his 1912 manuscript. Of course, he invented special relativity and published it in 1905. But in 1912, for charitable reasons, he wrote down a beautiful version, and it's here that he initially describes the Lagrangian equals mc squared, and this is the correction factor for depending on how fast the electron under consideration moves, and crosses it out and generates the E. So if you ever wonder where that cartoon comes from, it comes from here. It comes from Einstein himself. Now, the great discovery in 1887, 1888 by Michelson and Morley, mostly done at what is now the Case Western Reserve University in Cleveland in the United States, was that the speed of light is constant for all observers. What do I mean by that? Well, imagine that I take, if this were an American audience, I would say a baseball, but you guys don't play that here. So if I take a rugby ball, okay, and I fling it at you at some speed, at 30 miles per hour, and you're sitting still, well, you know, if I ignore friction in the air, the rugby ball will hit you at 30 miles an hour. But if you're backpedaling, if you're running away from me at 15 miles an hour, then the rugby ball coming at you relative to me at 30 miles an hour will only hit you at 15 miles an hour because you're running away from it. So speeds are additive, okay? But if I fire photons at you, they leave my flashlight, my laser pointer, at the speed of light, which is about 300,000 kilometers per second. And if you have a speed meter and you're able to measure the speed of the photons hitting your hand, it'll be 300,000 kilometers per second if you're standing still. And you would think that if you were moving backwards at 100,000 kilometers a second, then you would only measure the speed as the difference, 300 minus 100, 200,000 kilometers a second. Bzzz, wrong answer. You still measure the speed as 300,000 kilometers per second. That's a crazy result. That's totally counterintuitive. It's different. Light is different from everything else. So the speed of light is the same for all observers. This was demonstrated in 1888, and physicists were driven half mad by this. They really were. Now, the way this experiment was carried out was by using a source of light. Today we would use a laser, of course, and shining it through a piece of glass. We have a beam splitter, so half the light goes this way, half the light goes that way, and then the light comes back and recombines on this detector. And what you're seeing on the detector is an interference pattern, so you can measure very tiny differences in the speed of light between light going this way or light going that way. Well, why should light go at different speeds in different directions? Well, imagine that you're moving through some medium, that you're not stationary, but you're moving through the ether, not the ether that knocks you out, the AETHER, a hypothetical medium through which light propagates. Why would physicists need ether? Well, think about it. Light has many wave-like properties, as does sound. Okay, the reason you can hear me is because my vocal cords are producing pressure waves in the air, and those pressure waves are moving out through the air to you. So for sound to work, there has to be a medium, namely the air. Remember, space, nobody can hear you scream. So there has to be some sort of medium to propagate a wave. Well, if light is a wave, therefore, there has to be a medium. The medium is the ether. We have no idea what the ether is, but we hypothesize it's there. Now, if there is an ether, then there is an upstream and a downstream and across the stream through the ether. And so sound, okay, if I'm moving towards you, can seem to be moving certainly with different frequencies, and light moving with the flow of the ether or against the flow of the ether should be moving at different speeds. And so the beautiful experiment that was conducted here was to take this massive block of granite, so everything was very stable, shine light up and down through the ether and across the ether, and then rotate the table to look for changes in the speed of the light that was moving this way or that way. And what drove the physicists half mad was that there was no change. Absolutely constant. And they built better and better and better and better versions of the experiment and could find no change at all. Now, how could that be? Because we're moving. Remember, the Earth is moving around the sun. Even in 1888, people knew that that was a true statement. And they knew how fast we were moving, okay? We were moving at 30 kilometers per second. We were moving at that speed then, and we're moving at pretty much the same speed today. So something was seriously wrong, and Einstein was able to take this and say, you know what? The experiment is right. The speed of light is the same for all observers. This is the experiment. But if this is true, I'm now going to rattle you to your core. Because the only way this can be true is if clocks don't tick at the same rate for all observers. Sounds crazy. If you and I synchronize our watches, and then we just sit here, and our watches are really good, if they're atomic clocks, then our watches are going to keep on ticking away at the same rate. But what Einstein tells us is that if I take my clock and I leave the room, run around the building and come back, my clock will have ticked less than yours. So your state of motion determines how fast your clock ticks or how slow your clock ticks. And clocks tick at different rates for observers in motion relative to each other. That's the logical consequence of what this is. And that's a scary thing, because it means that everything in the universe, everything that we believe in, is relative and not absolute. Time is not absolute. Time is relative. Okay? And if that's true, then the ground on which we've always walked since children, namely, let's synchronize watches, okay, doesn't mean anything anymore. Your watch can suddenly run fast, mine can suddenly run slowly. Now, happily, the major differences that are predicted by this only happen near the speed of light, and we can't move yet at close to the speed of light. But we're going to get there, okay? We're getting faster every day. In 4, 5, 6 centuries from now, Star Trek-y stuff will seem old hat, and relativistic effects are going to play vastly important roles, I think, in human history and human society. There's Einstein visiting Caltech in 1931 with Albert Michelson, one of the 2 designers of this magnificent experiment, and with Millikan, who was the first person to measure the ratio of the charge to mass of an electron. Now, here's what Einstein said, and here's why what I just told you works. Einstein did a Gedanken Experiment, a thought experiment. This is a device you could never build. Well, you could if you had enough money. You could build such a thing. You take 2 mirrors, and you make them very, very highly reflective, and you put them 93,150 miles apart. Why 93,150 miles apart? Because it takes exactly half a second for light to travel from this mirror to that mirror. Every time the photon hits this mirror, the mirror says tick. And every time the photon hits that mirror, the mirror says talk. So I have a clock. Tick, tock, tick, tock, tick, tock. Okay, every half a second I've got a tick and I've got a talk. Now, if I'm standing still, okay, now I'm the observer, and I'm looking at the clock, and I'm standing still, and I synchronize my watch with that clock, and we're both going to tick-tock at the same rate, because I'm not moving relative to the clock, okay? Now, let's say I decide that I'm going to go whizzing by the clock at high speed, or better still, I'm going to stand here, and I'm going to let the clock whiz by me. So I'm going to be in a different state of motion, not accelerated motion, constant velocity, constant speed relative to this clock. What will I see? What am I going to see? Well, that's what I'm going to see, okay? I'm actually going to see the photon bouncing between the mirrors, but because the mirrors are moving to the right rapidly with respect to me, I'm going to see the photon moving along this diagonal path, H for hypotenuse, okay? And we all know that the hypotenuse is longer than O, the vertical distance. Now, the person who is standing on mirror 1, or moving at exactly at the same speed as mirror 1, sees the photon bouncing up and down, and sees a tick and a talk, and the distance that the photon has to travel is O. It's a small distance. And so, okay, by implication, if it's a small distance, then the ticks and talks happen rather quickly. For me, I see H a longer distance, and the ticks and the talks happen more slowly because I'm waiting longer for the photon to get up there and then to get down. It has to travel further. Photons travel at the same speed. I see light traveling at the same speed as that moving observer. As a result, my clock and the person traveling rapidly by me don't see time elapsing at the same rate. That's the fundamental reason. And this leads to what is sometimes called the twins paradox. Imagine two twins born by cesarean section, literally taken out of the mother's womb at the same nanosecond, okay? And one of them is instantly kidnapped by her nanny, taken on board a spaceship, and off she flies at 99% the speed of light to Alpha Centauri, 4 light years away. Well, the twin here on Earth grows at a certain rate, and she sees or knows about the spaceship receding at 99 or 99.99% the speed of light to Alpha Centauri. And when she reaches Alpha Centauri, the nanny has a change of heart and realizes that she's made a mistake, so she turns the spaceship around and comes back at 99.9% the speed of light. Well, the twin on Earth will be 8 years old at that time because it's taken light or something moving very close to the speed of light 4 years to get there, 4 years to get back. Okay? For the astronomers in the audience, yes, it's 8.6 years, but okay. So that's fine. What is the age of the twin on board the spacecraft? Well, depending on the precise speed at which she's traveled, she might be only a day old. She might be only an hour old. The closer that spaceship was to moving, the closer to the speed of light, the greater the time dilation effect is, and the less time has elapsed on board. Now, does that mean that everyone, the nanny and the baby on board, felt that they were moving slowly? No, nothing like that. You have no physical sensation that anything is different. It's just that the universe seems to be whizzing by outside you. They seem to have sped up and you seem to have slowed down. There are other strange effects of the universe collapsing in space into directions in front of you. Second order effects. This is the key thing, that time is not absolute. Now that scared the Nobel Academy. It scared all physicists. It scared the public. Well, it didn't really scare them. It just sort of, he's too smart. I can't understand this. But today, I think we can collectively wrap our arms around this. And there's so many experimental verifications of this, by the way, because instead of using twins, today we use muons, radioactive particles that are created in the upper atmosphere by the collisions of cosmic rays with atoms in the upper atmosphere. And we see that muons moving very, very, very fast, nearly at the speed of light, live far too long. In the laboratory, when we create them, they vanish in a 100 millionth of a second. And so the vast majority of them created in the upper atmosphere should never get down to the ground, but the vast majority do. And that's because their clock is tick-tocking very slowly relative to clocks on the ground. And there are many, many other experimental verifications. But the freakiest of all is an experiment done in 1997, where 2 atomic clocks were set up on the ground in a laboratory and synchronized with each other, and then synchronized with another pair of atomic clocks that were put on board a Boeing 747. Okay, so all 4 clocks were perfectly synchronized. And the Boeing 747 took off, and it flew around the world, took 2 days to fly around the world, and the 4 clocks were brought back together. And the 2 clocks on the ground were still perfectly synchronized with each other, and the 2 clocks on the Boeing 747 were perfectly synchronized with each other, but these 2 and these 2 were not synchronized anymore at all. Less time had elapsed on the 747 flying around the Earth than had elapsed on the ground, by exactly the amount predicted by Einstein's special relativity. Yeah. Time is not absolute. Time is relative. The faster you move through space, the slower you move through time. I'll say that one more time. The faster you move through space, the slower you move through time. There is a kind of conservation law there that is that everybody and everything moves through space-time, through this 4-dimensional construct of Einstein. Everyone moves through space-time at the same speed. But if you move through the part that we call space faster, you move through time slower, and vice versa. All right, let's go forward, please. So Einstein was asked by many people to explain relativity theory. And his explanation boiled down to this. Pretty girl sits in your lap for an hour, seems like a minute. You sit on a hot stove for a minute, it seems like an hour. That's relativity. Okay, here's the part of standing on one leg. About 10 years later, Einstein figured out how gravity works. Gravity is an extension, a huge extension, of relativity theory. In special relativity theory, he considered only observers moving at constant speed relative to each other. Now he was worried about accelerating frames of reference. And the core idea as to why gravity works is the following. It is geometry. And by this time, he was very comfortable with playing with 4 dimensions, not just the 3 spatial dimensions, right, left, up, down, sideways, forward, that we're accustomed to, but he thought of time in many ways as being that 4th dimension. And he said the following. Let's say I take a trampoline. So this is a trampoline surface, and the trampoline is under great tension, so it's absolutely flat. If I now take a little marble, a very, very lightweight marble, and roll it across the trampoline, the marble will follow a perfectly straight line because the shortest distance between 2 points is a straight line. Okay? The marble will follow a geodesic, the path of least resistance, that shortest distance. Now, let's do a little experiment. Okay? And what I'm going to do is I'm going to put a cannonball down in the middle of the trampoline. The trampoline is no longer flat. The trampoline is now got this dimple in it. It's got this curved shape because of this mass that's sitting in the middle of the trampoline. Space, or the surface of the trampoline, is no longer locally flat. It has curvature. It is bent because of the presence of this mass. Okay? Now I'm going to take my little marble, and if I roll it fast enough and far enough away, the marble doesn't feel the presence of the mass. But if I roll the marble closer, the marble now feels a deflection force in essence, because the surface on which it's moving is no longer flat. The shortest distance between 2 points is no longer a straight line. Shortest distance between New York and London is not a straight line, unless you can drill through the Earth, but let's not do that. If we're restricted to the surface of the Earth, there is a geodesic. There is that northern route, which takes us almost up to Iceland. That's the shortest distance between 2 points. Well, that's exactly what's happening here. The marble, if fired at the right direction at the right speed, goes round and round and round and round on the outside of this cannonball sitting in the middle. Now substitute the sun for the cannonball, substitute the Earth for the marble, and substitute space-time, this four-dimensional construct, for the trampoline, and you suddenly understand why the Earth goes around the sun. The Earth orbits the sun not because there's a magic arm reaching out from the sun to the Earth. There's no action at a distance. The Earth orbits the sun because the sun warps space-time, bends the geometry of space-time around itself. And so the Earth has no choice. The Earth wants to follow the path of least resistance, the geodesic, and that's the path that the Earth takes around the sun. So gravity is because of geometry. Gravity works because of geometry. The warping of four-dimensional geometric space-time is what gives rise to gravity. And now you all understand general relativity. Now, there are details. And of course, the devil is always in the details. But nevertheless, that's the core idea. That's the fundamental idea. Now, any theory, no matter how beautiful, how expressive, how explanatory, is nothing but hot air unless you test it. You've got to have experimental verification. That's the name of the game in science. And before you can have experimental verification, you've got to have predictions. So in 1913, here's the date, Einstein makes a prediction, and he says, because the sun, der Sonne, S-O-N-N-E is the sun, has gravity, and because it's bending the space around itself, anything moving by the sun will be deflected, including light. So the sun is going to be a light deflector, and the sun can actually, in a sense, concentrate light. It can act like a magnifying glass. It can focus light, or bend light, or deflect light. And the important thing is not just to say that, but to make a prediction. And Einstein predicted that the deflection of light would be 0.84 arc seconds if we were at the Earth, and observing a very, very distant star. Now that's the wrong answer. It turns out to be the wrong answer. The angle is actually 1.75 arc seconds, and he caught his error. He found his error next year and updated his prediction and said, whoops, got it wrong. The real answer is 1.75 arc seconds for a star that's right near the sun. Terrific. How are you ever going to observe stars next to the sun? Has anyone tried to do that experiment recently? You're not going to be very successful unless you do what the experimenters did, the astronomers did, and that is go wait for a solar eclipse. Now, if there's one thing astronomers do know how to do, it's predict when eclipses are going to happen, when and where. We've known how to do that pretty much since the time of Newton, or just a few decades later. And so if you wait for an eclipse of the sun, you're also going to be able to see the stars, there they are just very faintly seen, outside of the corona of the sun, when the moon passes right in front of the sun. So the idea is to go on an eclipse expedition to some exotic, wonderful place, set up your telescopes, take pictures of the sun during the eclipse, and then set up the same camera, the same telescope, the whole same 9 yards, and do it again 6 months later, or 6 months before, it doesn't matter, when the sun isn't there, when the sun is on the other side of the sky, because the Earth has gone around the sun, and take pictures of that star field. And Einstein said that stars right at the limb of the sun will actually appear to have moved outwards from the sun. Why? Because of the geometry. You see that the Earth is here, and the light has been deflected this way, and so if we go backwards along the dot, 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 dot line, that's where we think the star is. when in fact the star is here. So stars are bent outwards, and the further away you are from the sun, the less the deflection. So you need to take photographic plates during an eclipse a few months before and compare the two and work out the answer. And I would love to say that astronomers got it right the first time. It's a very difficult experiment to do. And of course, travel in 1919 was not a piece of cake. This is right after the First World War. The world was still pretty much in chaos. And of course, wherever you know you're going to go, there's always a chance of clouds, and your telescopes break, and blah, blah, blah. The stuff that astronomers moan and groan about all the time. And all of that bad stuff happened, and nevertheless, there were still pretty good results, pretty definitive results, which demonstrate that Einstein was right. And he became a media darling and superstar almost overnight. He became the most famous person in the world when the results were announced in 1920. He was the right person at the right time with the right idea. The world was sick of the previous world order that had been maintained for centuries across Europe. So many millions had died, and people began to see that so much of it was so terrible and such a waste. They wanted something new. And he was just the right guy in the right place, right time with the right idea. Funny thing about all of this was that he also predicted that this bending of light would give rise to an effect that today we call gravitational lensing, or the focusing of light. And he knew this, and he talked about it at seminars all the time. It was sort of a 3-minute throwaway. He derived two very simple basic equations that basically told you how much things got bent and what it depended on. And he was bored with it. After he understood it, he understood gravitational lensing. It was like a complete afterthought. It wasn't even worth an appendix in one of his less notable papers. So there was a Hungarian physicist who drove him mad for nearly 15 years, kept pounding away at him. This is important, this is important. Einstein said, you're crazy. No one will ever observe this. It's impossible. The effect is so tiny, it's so infinitesimal, it's just a waste of time. Finally, he wrote the paper down. Here's the whole paper. This is the entire paper. There's this discussion. It ends right here, followed by Pleistocene Man in Southern California by some paleontologist in Science magazine. And he submitted it to Science, and he had a little cover letter to the editor that says, look, there's this nuisance physicist who's driving me mad. This paper is of no value, but please publish it anyway. Just do me a favor, get him off my back. And that's what Science did. Well, let's fast forward about 2 generations, and there is something that is today referred to half-jokingly by astronomers as the Einstein cross. And when you look really carefully at the Einstein cross, I don't think the room is dark enough, but never mind. It's at the center of a galaxy. You see, what's happening is that there is a very, very distant source, a quasar, that is behind a very luminous source of light, which is behind the black hole, the supermassive black hole sitting at the center of that galaxy. And the light from that source is being bent, being deflected by different amounts in different directions and forming 4 images. So 1, 2, 3, 4. Each of these, 1, 2, 3, 4, is really the same source imaged in different ways by the supermassive black hole at the center of that galaxy. And this has become more than a cottage industry. The deflection of light by matter gives rise to an important suite of beautiful things that we see. In particular, every one of these arcs here is a very, very distant galaxy, much further away than this or this or this or this. Each of these yellowish orangey blobs is a galaxy in a very large cluster of galaxies relatively close to the Earth. But when you image, especially with the Hubble Space Telescope, you can begin to see these gravitationally lensed arcs. And perhaps even more fascinating, more important, is that we can begin to map out the dark matter. There is vastly more dark matter, you know, in the universe than there is ordinary matter, stuff that we're made of. And the dark matter can be mapped out, its distribution and how much is there, by this process of gravitational lensing. And this is an Einstein throwaway. This was, as far as he was concerned, a junk idea, hardly worth the paper on which it was written. Well, another thing that emerges immediately from general relativity, and this was worked out by a German physicist on the front lines in Russia in the First World War, Karl Schwarzschild, is that if you solve Einstein's equations, the ones that he wrote down in 1915, you see that there are simple solutions, algebraic solutions to these equations that give rise to a description of space and time that lead inevitably to the idea of black holes. So black holes pop out of general relativity in a very, very natural way. The prediction that they must exist and the predictions of how objects must move around black holes. Do we see such things? Well, you know, of course not in 1915. The technology didn't exist. But by the 1970s, when we got above the Earth's atmosphere with X-ray detectors and then gamma ray detectors, we see that there are black holes everywhere in the universe. That the center of almost every galaxy, not every, but the center of almost every galaxy has a supermassive black hole at its center. And the way you see that, at least in the simplest case of a binary star system, is you have either a black hole or a very compact object like a neutron star acting as a kind of vampire, sucking hydrogen off the surface of an ordinary star, drawing it into an accretion disk, and that stuff falls down onto the black hole. We've seen some recent representations of this in the movies, some of them rather good, I must say, in the movies. The idea that such crazy objects could exist, or that they are as important as they are in the universe, comes directly from Einstein, from general relativity. If any astronomers or any physicists had any doubts about the reality of black holes, I think they were put to bed forever in 1997 by this image and this spectrum taken by the Hubble Space Telescope. This is the nucleus of a giant elliptical galaxy in the Virgo cluster, Messier 84, and there is this bright spot, and when you put a slit of a spectrograph of the Hubble telescope across that center, what you're doing is actually acting like a policeman with a radar gun. You're measuring the speed of matter moving around that center of the galaxy, and you see that the speed is not so great far away from the galaxy up here, and then as you approach, you suddenly get enormously blue shifted, and then red shifted, and then back again. And this colossal change in velocity from stars moving at you at tremendous velocity to stars moving away from you can only be understood in terms of a disk of matter, okay, orbiting that object. And the object at the center of this galaxy has to be about 1 billion times the mass of the sun, and it can't be much bigger than our solar system. And the only thing that matches that is a supermassive black hole. I'm going to go back to Einstein and his life at this point. I'm going to stop with the physics, even though one could continue for many hours. And I haven't covered all the other branches of physics in which he made such seminal contributions. But I wanted you to have a taste, a flavor, both of the fundamental physics and of the astrophysics. And modern astrophysics really would hardly exist without Einstein, to understand some of that. But I want to go back to Einstein, the man. In 1933, he was visiting Caltech when the Nazis came to power. Einstein was on their death list. He was warned that if he returned to Germany, he'd immediately be thrown into a concentration camp or executed. So he stopped here in the UK while his friends frantically tried to arrange for an American visa for him. Finally, they did manage to arrange it, and he went back to the United States, where he lived for the rest of his life, from 1933 to 1955. He adopted Princeton University in the town of Princeton as his home. People there were very, very welcoming, and they gave him space, too. He really didn't want the celebrity wandering around in Pasadena, in Los Angeles. People would often come up to him, ask for his autograph, engage him in conversation, and he wanted a bit of privacy, and that happened in Princeton. Now, one of the core principles of general relativity is the principle of least action, or the lowest energy state into which things can fall. And Einstein loved to say of himself that the reason that his favorite sport was sailing, and he was an avid sailor, though, again, not a very good one. He often ended up in the New England Sound. But the reason that he loved sailing so much was because it was the sport which requires the very least amount of energy, the least expenditure of energy. By the time of 1939 had rolled around, the Second World War broke out, and Einstein had been a pacifist all of his life, and he had to make a decision. Was he going to continue down this path or not? And just before the outbreak of the Second World War, he was faced with one of the hardest decisions of his life. He had become, or was just about to become, an American citizen, and a very loyal citizen. But in late July, some of his colleagues approached him and said, listen, we are aware of physics experiments going on in Germany that are going to lead to a new kind of weapon. And unless the American government is made aware of this, and we humble little physicists have no voice but you, the United States might be destroyed and the Nazis might conquer the world. So Einstein writes to President Roosevelt, and he says, some recent work by Fermi and Szilard has been communicated to me. In the course of the last 4 months, it's been made probable through the work of Joliot in France as well as Fermi and Szilard in America that it may become possible to set up a nuclear chain reaction in a large mass of uranium by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain this could be achieved in the immediate future. Well, so what? This new phenomenon would also lead to the construction of bombs, and it's conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by boat and exploded in a port might very well destroy the whole port together with some of the surrounding territory. What an understatement. What an understatement. But nevertheless, the idea that the element uranium was essential and that this could lead to bombs is contained in this letter written to Roosevelt and today held at the Roosevelt Presidential Library just north of New York City. And again, one of the really precious artifacts I was entitled to hold in my gloved hands for a few minutes. And the response from Roosevelt to Einstein is, my dear professor, I want to thank you for your recent letter, most interesting and important enclosure. And he promises that Dr. Sachs will cooperate and work with a committee, set up a committee to look very, very carefully at the element uranium. And this, of course, is the beginning of the Manhattan Project. The realization within the American government that this is a do-or-die situation. And so in this sense, Einstein is the godfather of the atomic bomb, or perhaps the handmaiden, or what have you, or the midwife. But of course, he's completely barred from working on the Manhattan Project because he's considered a security risk. So even though he's the one that warns the American government, warns the president, gets everyone understanding that this is a real problem, he doesn't know anything about Los Alamos or the work that's going on in the desert or the explosion of the first bomb, the Trinity test, nothing. He's utterly unaware of this. And so when he was asked some very, very bitter, angry, pointed questions after the Second World War by Japanese reporters, why did you participate in this? And he said, I saw the imminent destruction of humanity by the Nazis. They were working on this, and the reason I informed the American government was that there was no choice. If I did not do this, if the American government took no action, the world might well, as we knew it, might well have been destroyed. Well, E equals mc squared, remember that cartoon at the beginning? It's not such a cartoon, leads to this. It means that a kilogram, just like a dollar equals a British pound, okay? $1.5 equals a British pound. 1 kilogram of matter equals a vast amount of energy because of the c squared, the one with 21 zeros. The conversion factor is vast, and it leads to things like this, which are terrible, but it also leads to understanding this, which is wonderful. Science is always a two-edged sword. The reason that the sun shines is because the sun is converting hydrogen into helium through fusion, releasing gamma rays in the core of the sun in the form of energy. Those gamma rays trickle out to the surface of the sun. Takes about 30 million years. Lots of scatterings before that gamma ray gets out to the surface, but never mind. And the sun is shining because there are nuclear reactions and the conversion of matter into energy in the core of the sun. About 0.7% of the mass of 4 hydrogen atoms is converted to gamma rays, to energy, in the production of 1 helium nucleus. This also means, of course, that the sun has a finite lifetime. The lifetime of the sun is about 10 billion years. Not million, billion, the American billion, so 1 with 9 zeros after it. That's the expected lifetime of the sun, about 10 billion years. It's about 4.5 billion years old now, which perfectly matches, not perfectly, almost perfectly matches the age of the oldest rocks on Earth, which are 4.0 billion years. And it beautifully matches the ages of the meteorites that fall to Earth, which are 4.567 plus minus 0.001 billion years. Spectacular agreement. The solar system is created pretty much at the same time. The sun is just one of 100 billion or 200 billion stars in our galaxies shining by nuclear fusion. Now, as Einstein grew older, he in many ways grew apart from the physics community. He was looking for a grand unified theory. He was trying to explain all of physics, not just gravity, but electromagnetism. And of course, during much of his lifetime, the strong nuclear force and the weak nuclear force were unknown. There was no understanding of nuclear reactions. Today, one would want to unify all 4 forces into one theory, and there has been a great deal of success in unifying the strong nuclear theories, weak nuclear reactions, weak nuclear forces, and electromagnetism, but gravity stands apart. And the unification of quantum mechanics, the physics of the very tiny, and of gravity, the physics of the very, very large, is not yet there. We all hear about, or we hear a lot about string theory. That might be the grand unifying theory, but it hasn't gotten there yet and has not yet made a testable prediction. Lots of post-dictions, but no successful predictions yet. During this time, of course, Einstein was the most famous physicist on Earth, and many people came calling, amongst them David Ben-Gurion, the father of the State of Israel, a great admirer. And one of the things that happened, and Einstein was a strong supporter of Israel. He wanted a homeland for his people who had been so badly massacred by the Nazis. He was actually asked to become the president of the State of Israel in 1952 after the first president. President is an honorary title, an honorary head of state. He declined, was very distressed to do so. A more interesting story, perhaps, is that David Ben-Gurion and Abba Eban, who was the foreign minister of Israel, debated back and forth between them as to whether to even offer this to Einstein. In the end, they decided it would be a good political move, so they did so. But Eban is reported to have said to Ben-Gurion, "Oh my God, what do we do if he actually says yes?" Einstein had the good sense to say no. Einstein also consorted a lot with subversives. Anyone recognize this subversive in the picture? Charlie Chaplin, of course. And there he is at the opening of City Lights in 1931. This is while he was still a visitor. He drew bigger crowds than Chaplin did, and bigger crowds than anyone else did. One of his finest hours was 1952, 1953. McCarthyism, this idea that there were communists hiding under every bed in the United States, infected much of the United States, the American psyche, and there were real demagogues, people like Joe McCarthy, who were stoking these fears. Einstein made it very, very clear, abundantly clear in his writings, that if called to testify before one of these committees, he would basically tell the committee to take a hike or to go to hell. He was disgusted with what was going on in the American political process and let this story be published in the New York Times, basically saying, "I dare you. Come get me. Okay? I am prepared for financial ruin. I'm prepared to go to prison. But what you are doing is destructive of our democracy." Truly one of his finest hours. And happily, sanity overtook America about a year or two later. He died in 1955 of an embolism. He, in some sense, had run out of steam. He was 76 years old. He had smoked a pipe all of his life. His greatest exercise was sailing. So I guess he had reached his time. But he was working on a grand unified theory literally on his deathbed, just a few hours before he died, completely engrossed in physics and what future physics could mean. His whole life really was a work in progress, understanding the universe. And he leaves us, I'm going to leave you with just two quotes. This one resonates a lot with physicists. What really interests me is whether God had any choice in the creation of the world. And what he really meant by that was, does the universe come into being, come into existence spontaneously? A question that we can't answer today. And hopefully the next great theory of physics will give us some idea, some predictions, maybe even some testable predictions about this. And finally, I have no special talents, he said, but I am passionately curious. So I thank you for bringing your curiosity here tonight, and I'd be pleased to take any questions that you might have. Thank you.